It's a real pleasure to be here today, and I'd like to thank CNE News. It is an honor to be considered amongst these excellent chemists. Today I'm going to talk a little bit about how I became interested in environmental chemistry, and then a little story from my group looking at some of the Arctic work, since I know it's been hyped. All right, but first, my start in science came very early. My dad spent his career as a high school biology teacher, and he's very enthusiastic about science and enthusiastic about getting other people enthusiastic about science, and of course that meant me. So I spent a lot of my childhood outdoors looking at rocks and plants and bugs and all kinds of different things, and that really gave me a passion for both science and the natural world. And so I knew I wanted both of these things to be a part of my life. I didn't really have too much direction, but I knew I was really interested in biology, at the start at least. And I was fortunate as a high school student to be able to work in 2 real research labs, both with a biology slant. So I worked in a molecular biology biochem lab as well as a genetics lab. And I learned a ton about science. I really enjoyed the science, but the research, not as much. None of my proteins ever expressed. And I remember the moment when I realized that this biological research wasn't for me, when one of the graduate students in the genetics lab said that whenever he closed his eyes, he saw worms. And I was like, this doesn't sound like a really great path for me. So when I started my undergraduate degree at the University of Toronto, I was really open-minded about the type of science that I might like to pursue. And around that same time, the Department of Chemistry at the University of Toronto was developing an environmental chemistry program. This was the first time I'd ever heard about environmental chemistry. It's not that common in chemistry departments, and certainly wasn't at that time. And it really encompassed a lot of the things that I was passionate about. It's a rigorous science. You get to learn about the natural world. And which I thought was really great, you also can have the opportunity to influence policy and thus influence the natural world. So I started working as an undergraduate student in environmental chemistry labs, and I never looked back. I continued on at the University of Toronto in their environmental chemistry program as a doctoral student, and then went to a postdoctoral fellowship jointly between NOAA and the University of Colorado before starting my independent career. All right, so environmental chemistry is a diverse field. I really like this framework for how we approach environmental chemistry. This was developed by John Abbott a few years ago. And the idea is that we have 3 independent approaches that are really complementary and allow us to understand environmental issues. So the first is our lab experiments. So we try to simulate the real environment in the lab. For atmospheric type chemistry, we can do that in chamber experiments or in flow tubes. But of course, we can never fully simulate the complexity of the real environment. So that means we have to make field observations. And so this is where environmental chemists really get a lot of press because it looks glamorous, even though sometimes it's really not. We can collect samples from aircraft. One thing I did in my postdoc was put instruments on an elevator that went up and down a 300-meter tower. We collect samples from remote environments. And we try to really accurately characterize the chemistry in the real environment. And then the last leg of the stool is the modeling. And this is really essential to tell us if we accurately understand the chemistry happening in the real environment with the chemistry that we've tested in the lab. So these 3 together make up the 3-legged stool. Now, of course, any one person can't do all 3 of these things, so that means we have to do a lot of collaborating. In my group, we really work with state-of-the-art analytical tools. We develop them and we use them, and we try to push the boundaries of the measurements that we can make. And that means we're focusing mostly on the lab measurements and the field measurements, and then we have to collaborate with modelers to really complete the picture. So in my group, we work on several diverse problems. The way I like to approach this is to look for interesting problems in environmental chemistry and determine whether we have a useful measurement that could advance that field. So one of the things we're looking at is the chemical drivers of climate. We're really interested in characterizing absorbing aerosol. Biomass burning releases a bunch of stuff that we don't really understand that well, particularly brown stuff. And so one of the things that my group is doing is trying to deliver new analytical approaches to looking at these complex mixtures. We're also interested in air quality, both indoors and outdoors, particularly looking at initiating steps of oxidation and focusing on the role of chlorine in that oxidation. And lastly, we're also interested in the fate and transport of contaminants, really trying to understand how things that we use in our daily lives make it to the Arctic and other such places. So what I'm going to do for the rest of my time is talk about one example of the type of research we've been doing, looking at a class of chemicals and how they've become globally distributed. All right, so most of you, as readers of C&E News, are likely somewhat familiar with PFAS, perfluoroalkyl substances. Over the past couple years, C&E News has published numerous excellent articles about this topic, a few of which I've shown here. There was actually one in the current issue as well. So PFAS is really kind of an umbrella term, and it describes several different families that have different chemical properties. And although the title says perfluorinated, they're not actually all perfluorinated. Some are polyfluorinated, and this is very important when we think about the chemistry. So these PFAS compounds are really used in two major commercial applications. They're used in fire suppressant technologies as well as nonstick applications. So the real stars of the PFAS show are really the perfluorinated acids. So we have two flavors of these. We have the perfluorocarboxylic acids and the perfluorosulfonic acids. And these are perfluorinated, so that means they're very persistent in the environment. In the media, they're often called forever chemicals. And so these are of primary concern. And my interest in this, and where the detective story, I guess, really comes in, is the fact that we see these compounds in virtually every sample we look in. So we see them in the remote Arctic, we see them in the remote Antarctic, we see them in the middle of the ocean, pretty much everywhere. And this is not really what we would expect based on the chemical properties of these perfluorinated acids. So these acids, as the name suggests, are acidic. They're quite strong acids. The carboxylates have a pK of around 0. The sulfonates have a pK of around -8. And so these can actually be directly emitted from industrial processes. But we expect that because they're highly water-soluble, strong acids, they're going to rain out quite quickly. So we wouldn't think that this could be a way they could be globally distributed. They can also be emitted directly into aqueous systems through industrial processes or the use of consumer products. And this is really what has led to the media frenzy, I would say, over the past couple years, looking at these compounds because there's a big issue of exposure for people living in areas that have been contaminated by these compounds. All right, but that's not what I'm going to be talking about today. My interest is really in these polyfluorinated compounds that are volatile, and because they're polyfluorinated, not perfluorinated, they can undergo chemistry. So these volatile compounds, we expect, can live in the atmosphere, and because they can live in the atmosphere, that means they can travel long distances. These compounds can, again, be emitted from industrial processes or from our use of consumer products. And so what we really wanted to test here, using our three-legged stool approach, was whether these volatile PFAS compounds could be playing an important role in the long-range global distribution of these perfluorinated, persistent PFAS compounds. Okay, so the first leg of the stool is looking in the lab. And so I'm just showing an example here of the type of experiment that we've done. This is a polyfluorinated compound that's an important PFAS precursor. And so we put it into an environmental chamber and subjected it to the types of reactions we would expect to find in the environment. So we subjected it to photolysis, reactions with chlorine atoms, and reactions with hydroxyl radical. This environmental chamber has in situ FTIR that allows us to monitor the reactions in close to real time. And then we were able to distinguish a single primary product, which is a fluorotelomere, a polyfluorinated aldehyde. And under continuous reactions, some of the same reactions, reactions with oxidants or photolysis, we end up with these perfluorinated compounds. So we were able to take a polyfluorinated compound and convert it into perfluorinated acids using the types of reactions that we would expect to find in the real environment. okay, so that's a lab environment. We might be making some assumptions that don't apply in the real world. So we want to make sure that we have real data to back this up from the real environment. And the samples that we collect to do this are ice cores. So we have 2 ice cores that we've been working with recently, one from the Devon Island ice cap and one from the Mount Oxford ice field. And we use ice cores because they're like a time capsule of atmospheric deposition. So they give us this record into the past, which we can really use to tease out potential sources. So this is not me. I'm not that cool. When I go to the Arctic, my photos are not that photogenic. They're just terrible, actually. So this is Ali Crisatiello. She's a glaciologist we work with, and she's really the one who we've been working with to collect the ice cores. She's obviously intense. All right, so then we bring these back to the lab, and they're quite challenging to work with. We have to keep them frozen. And the levels we're looking at are very, very low. So we're looking at parts per quadrillion levels. That's picograms per liter. And of course, almost anything that we have in our daily lives might have PFAS in it. So we have to be extremely careful when working with these compounds. And you can see one of my grad students here is really well equipped for sectioning the ice core in our -10 C clean freezer. And we then take our ice cores, we melt them, we extract them, we analyze them by LC tandem mass spec, and we eventually get to see a temporal trend of different perfluorocarboxylic acids that have been deposited to these remote regions. And we see PFCAs in all of our samples. We see generally it's increasing over time, but really what we're looking at here is tools to understand where these might be coming from. So we use the temporal trend. That's one of our tools. Another one of our tools is looking at the different ratios of homologs, because we can relate these back to the yields that we see in our chamber experiments and see if these make sense. And so from these deposition trends, we can say that the deposition is very consistent with what we'd expect from our lab experiments, indicating that our polyfluorinated PFAS compounds may be an important source to this region. But we're not done yet. We want to make sure that we actually understand what we're talking about. So we want to complete the stool by using the last leg, which is modeling. I'm not a modeler, but I collaborate with some talented modelers based out of MIT, Noel Celine and Colin Thackeray. And what they have done is take all of the chemistry that we understand from lab experiments and put it into a chemical transport model called GeosChem. And what they then do is predict the deposition of PFCAs that they would expect based on all of this chemistry. And we get something that looks like this, a deposition map, and we can then compare that to what we see in our ice cores. And we actually see really, really close agreement. So what this tells us is that our three-legged stool of modeling, lab work, and field all support our idea that these polyfluorinated PFAS compounds actually are important sources of these perfluorinated PFCAs to the remote environment. Okay. And with that, I'd like to acknowledge mentors, collaborators, group members, both former and current, the funding agencies that have generously supported my work, and thank you for your attention.